We know that designing processors is hard, expensive, and takes years, but does it have to? No. Codasip is a European IT company with a worldwide impact. We are passionate about what we do and believe that creating a superior processor core shouldn't be complicated. Our goal is to provide best-in-class tools and IP to make processor design simpler, faster, and cheaper. We achieve that with the help of the open RISC-V architecture and our patented design technology. Our portfolio works together in perfect harmony. Codasip Studio is a unique design automation tool. Codasip RISC-V processors are our range of processor IP cores. And Codal is a processor architecture description language. All Codasip RISC-V processors are written in Codal and can be easily customized in Codasip Studio. Everything you need for production is generated automatically, which makes the whole process very fast. Have your on-chip processing challenges solved. Get your core tailored to your project. Choose Codasip.
Hello everyone. Good morning or good afternoon. My name is David Luo. I'm from Mythic Incorporation. Today, I and my colleague, Dr. Zdenek Prikryl from Codasip, will jointly present this talk. Our topic is how to use and extend the RISC-V core in neural network applications using analog matrix processor. First, please allow me to give a few sentences for a quick introduction of both company. I'm from Mythic. My company's main focus is to develop and deploy the AI solutions in edge computing devices using analog computing-in-memory technology. Dr. Prikryl is from Codasip. Codasip is a leading provider of RISC-V processor IP and automation tools for designing and customization the IP core. The main SoC product from Mythic is called Analog Matrix Processor, AMP. Each analog matrix processor, AMP, contains a large two-dimension array of processing tiles, as shown in the image at the right side. The left image shows the structure of each Mythic processing tile. Each tile contains an analog compute engine called ACE, a RISC-V processor, a SIMD data engine, a scoreboard, and some amount of SRAM. Each tile also has a NOC router, which connects the neighboring tiles and form a two-dimension array. A Mythic analog compute engine, ACE, is one of the key components in our AI solution. It stores neural network weights in on-chip non-volatile flash memory, and it computes the matrix multiplication directly within the memory. This technique provides a significant power saving as well as a great performance enhancement in neural network applications. The RISC-V processor plays a key role in our analog compute engine. With the help from a hardware scoreboard, the processor manages the dependency of the data and the resource required by the neural network models. Since each neural network is naturally a data-driven processing flow, RISC-V core formats the workload commands based upon the data type and the resource availability. It issues such workload commands to the proper processing engines once their trigger conditions are met. Several key factors are taken into account when we select RISC-V from Codasip as our choice of embedded processor. First, the processor needs to have the ability to add customized instructions. Since we are running specific real-time loops controlling the data flow of the workloads, customized instructions helps us to improve the execution latency as well as reduce the memory footprint. For the similar reason, supporting low latency interrupt is also highly desired. Second, our architecture requires the processor to have a good idle power profile and a quick wake-up time when it is inactive and wait for interrupt. Last, it is obvious that we need a very cost-effective embedded processor in terms of a PPA, power, performance, and area, since tens or hundreds such cores are usually instantiated in our SoC solution. With all these criteria, RISC-V from Codasip nicely fit into our AI solution. Now, please allow me to turn to Dr. Zdenek Prikryl for the second part of the presentation.
Hello, my name is Zdenek Prikryl, and in the second part of this presentation, I'd like to focus on a contribution that the Codasip did in this project. Before we dive into detail, let me just briefly introduce our company. Codasip is a leading provider of RISC-V processors IP and the tools that you can use for customization. We have a wide selection of processors starting from the low-power embedded up to the application processors booting Linux in the multi-core cluster. We have also solutions for DSP or AI or other domains. As mentioned, we have tools that we can use for customization or modification of these processors. And in fact, it is the same tool that we use for the development. The concept is based on the high-level description language we use, and then the tools are able to generate all sorts of the outputs based on this input, including C compiler, RTL, and others. In this particular project, we started with the L30 RISC-V processor, which is one of our embedded cores. As with any other IPs that we have, is pre-verified in tape-out quality and it has standard interfaces such as AMBA, bus for the data and instructions, or JTAG for debugging. And the cores is, of course, configurable and customizable. By configuration, I mean that you can select from the options that we already verified and prepared for you, such as different memory layouts or different instruction sets that you can start with, like RB32, EMC, or IMC, or even with the floats. And customization means that you can change instruction set in the sense that you can add things there, you can add your own instructions, or eventually you can also play with the pipeline if you want to do that and add, for instance, coprocessor interface. The way how it works is that since the core is described in the C-like architecture description language, then we do everything there. It means that the description consists of the architecture part as well as the microarchitecture part. So we have instructions defined there, and we have also defined modules such as branch predictor, low store unit, or MMU. So as you can see, it scales well from the small embedded processors up to the application class processors. And again, in fact, every single IP that we have is described in this language. Then we give it to the Studio, and Studio generates all sorts of the outputs, including the SDK that consists of a C compiler, simulators, virtual prototypes, and so on. It also generates RTL, EDA scripts, integration test benches. And last but not least, it also generates verification tools such as UVM test bench or random program generator or consistency checker. As you can see, there is a loop back to Codal, which means that whenever you need to do some changes because you do some profiling, you just simply go back to Codal, change it, regenerate everything, and you can just inspect the new results. In other words, the compiler, RTL, other tools, everything is in the loop, which is quite convenient for design space exploration. Now, what exactly we did in this project is that we configured the L30 in a way that it's RV32IC, so no multiplication, no division. It is only instruction cache with the wide low store interface. By wide, I mean it's 256 interface. There's ONG debugger and, of course, low latency interrupts, which was the must to have for Mythic. This is the configuration part. Now, in the customization part, what we did is that we created the coprocessor interface because it was needed for that architecture. And we've added roughly around 70 instructions. DSP instructions, bitmap instructions, and also more complex instructions such as zero overhead loops or instructions that work with the coprocessor interface. All of that was done in the Codel language in the studio, and from the spec to verify deliveries, it was less than 2 months. So if you do the math, we were able to do more than one instruction per day, including other changes such as the coprocessor interface. And by the end, we had SDK, RTL verifications. Everything was in place. So to conclude this presentation, let me just highlight 3 things. One is that what's really nice about RISC-V is that it targets wide range of application, which is really a really good one. And it encourages people to innovate and differentiate through the custom instructions because by default, you have architecture license. And this is the advantage of RISC-V, and Mythic took this advantage because they integrated the RISC-V processors with the custom extensions to have a really, really nice solution that differentiates on the market. To do the design space exploration in the case of custom instructions efficiently, there should be some automation, and this is where Codasip plays an important role because we have tools that allows you to do this design space exploration quite efficiently, thanks to the fact that you have this description in a high-level description language that you can change easily, and you get all sorts of the outputs, including but not limited to C compiler, simulators, RTL, verifications, and so on. Thank you for your attention, and have a nice day. Good morning, good afternoon, or good evening, depending on where you are. My name is Zdenek Prikryl, and today I'd like to talk about RISC-V custom instructions and the way how you can create them. Before we dive into the demo, let me just briefly introduce our company and the methodology that we use for RISC-V custom instructions. Codasip is a leading provider of RISC-V processors IP and tools by which you can customize them or modify them. We have a wide selection of processors starting from the low-power embedded up to the application class processors booting Linux in the multi-core cluster. We have also solutions for DSP, AI, or other domains. As mentioned, we have tools that we use for modification or customization of RISC-V processors, and we use the same tool for creation of a new one. Now, the concept of this tool is based on the high-level description language in which we capture the CPU, and then we generate all sorts of the outputs, starting from the C compiler and up to the RTL. In this demo, let's focus on the modification, so how the modification is handled. As mentioned, the concept is based on the architecture description language, which is a C-like language. We call it Codel. And in this Codel language, you capture the architecture as well as the microarchitecture of the processor. In other words, you capture the instruction set as well as other blocks such as branch predictor, load store units, or MMU. As you can see, it scales well from the small embedded processors up to the application class because we have all these solutions, and it's possible to capture these processors nicely. And as already mentioned, every single IP that we have is designed in this language, and then it's prepared, it's ready for the modifications. So assuming that you have this code description, then you give it to the Studio, and Studio generates all sorts of the outputs. It generates SDK that consists of a C compiler, assembler, disassembler, profiling tools, debuggers, and so on. So pretty much everything that you need for software development. It generates also the RTL, EDA scripts, or integration test benches, everything that you need for starting working on the RTL level. And last but not least is that it also generates tools for verification, starting from the UVM test bench. Then you have tools such as random program generator or consistency checker. As you can see, there is a loop back to the Codel model from the outputs, which means that if you need to do some change, for instance, if you would like to add a new instruction, then you go to Codel, you regenerate all the source of the outputs, and you can inspect the results. So you can see that the SDK, including the C compiler or RTL, is in the loop, meaning that whatever you do, you have the results immediately and nicely. In this demo, we will use L30, which is one of our embedded core. And as a software, we're going to use just a basic FAR filter. The purpose of this demo is to focus on the way how you can add custom instructions rather than squeezing every single cycle that you can do. Also, I'd like to mention that in this demo, because it's just a minute, we will focus on the architecture portion rather than the microarchitecture. So let me switch to the studio. What you can see here is two projects. We have our software project, the core. Let's start with the software project first. So let's see where we stand if we use the standard core. So let's compile this software piece using our L30 toolchain. If I do that, I have my application ready and I can do profiling. So let's profile this application. I have prepared this one, so let's see where we end up. And we end up having results back in a little bit more than 17,000 cycles. And if you look at the source code coverage, we can see that the majority of the time is spent in the filter itself, which is not that surprising. But what we can do as well is that we can see and look at a code and try to find out what we can do with that. If I open the implementation and if I enable the annotations, I can see where the time is spent, which is of course this inner loop. If I move a mouse pointer to the line, I can see that I have two loads because I'm accessing two items in an array, and I have a multiplication and addition. So I can see here that I can do instruction fusion. I can create a multiply and accumulate instruction here. So let's do that. As a next step, I need to go and change the model. If you look at this structure here, we can see that we have the instructions for compact, for the extension. We have instructions for the integer part. We have instructions for the multiplication and division. And then let's focus on this file, which defines the first extension, which is our multiply and accumulate instruction. What I did here is that I prepared this instruction. It uses 3 register operands. So we have the source 1, source 2, and destination, and the destination is source 3 at the same time. In the assembly, in the text, it's very simpler. So we have MAC, then we have a destination, comma source 1, comma source 2. In the case of the binary, we follow what the RISC-V specification tells us. So we have our custom opcode, the major opcode here. We have a destination register, opcode of the MAC, source registers, and just second part of the opcode of the MAC, which is all zeros. And then more importantly, if you look at the semantics, what we can see here is that we are reading the input from the register file, and we do the job, which is in this case the multiplication and addition, and then we do the write back. Now these functions are already existing functions that we wrote, basically just reading the register files and some printouts as well if we enable them and so on. We have the main job here, and because we are targeting the low frequency, we can afford to have the multiplication and the addition in the same cycle. So I have it. So let's see where we stand if we add this instruction. What I need to do is I need to change the SDK. So let's change it to the first extension. If I do that, I can just simply recompile the application. And if I compile the application, I can just profile it again. So let's do that. When I profile that, I get the result where I can see the speed up already. So by having this single instruction, I have a speed up. So instead of a 17,000, I have a 15,000. If I go back to the C code to see where we stand and move mouse pointer here again, I can see that the MAC instruction is here mentioned because the compiler is smart enough to use this instruction automatically without any hint. If I look here, I can see that the clock cycles is reduced, but again, kind of obvious that the next step would be the load with a post increment. So let's try to do this addition as well. And to do this extension, it's a very similar story to what we did previously. So we are creating our new instruction. In this case, we are having the three kind of floats. So we have the byte, half word, and the word with the post increment. And then we have a destination register in the assembly, comma, source one, comma, and then the offset that we're going to use for the increment. In the binary, it's very similar. So we have our opcode for the major custom instructions, destination, one of these three instructions, then address, and then the immediate itself. In the semantics, it's nice to see that we have the address. In this case, it's simple. We just read the register. Then we're gonna use the load store unit that the CPU already has, and we just load the value. And then we just gonna add the offset to the address, so basically the increment, and write the result back from the load store unit. That's all I need to write here in this part, and I can try to do the same experiment again. So what I'm going to do is I'm going to change the SDK to the new one, recompile the application again, and profile it again. So if I look at the result, I have nice, 11,000 cycles now, which is like 30% faster than the previous case. And if I go back to the C code, right now I can see that the time that is spent here, it's really smaller. It's not more than 7,000. Right now it's less than 2,000, so it's not red anymore. I can do other optimizations, of course, but since this demo has just 10 minutes, so let's stop here. So to conclude this short demo, let me just highlight two items. One is that the RISC-V targets, in general, targets a wide range of application domains, including but not limited to AR, machine learning, DSP, small microcontrollers, application class processors, a lot of things. And one of the key things that RISC-V enables is customization. So the users or companies are able to add a key differentiation points or innovate through the custom extractions. Basically, this enables us to enter the heterogeneous compute world quite efficiently. Now, to be able to leverage every single possible thing that you have in a custom instructions world, then you should have some tools that helps you with the design space exploration. And this is exactly what the Codasip does, the Studio does. So using a combination of RISC-V and the Studio allows you to do really fast and productive design space exploration, finding the key differentiation points, and therefore have a better product in the end. Thank you for your attention and have a nice day.